Okay, hi everyone, welcome back. We are picking up our conversation on convolutional neural networks. Today we'll look at a couple of things that we couldn't get to last time, and most importantly, we'll look at backprop and conv layers today. The full derivation is in the notes, but we'll walk through a couple of steps and some intuitions of pooling layers and fully connected layers as convolutions. So let's take a look at a recap from last time and pick up on our discussion from there. So we introduced the notion of convolutions in the context of deep learning, which is really cross correlation. We have our operating sort of computational object, if you will, this expression right here. And today, actually, we will talk about backpropagating through this expression. And we'll talk about how to do at least one direction of one step of backprop. Backprop with respect to W and with respect to X. We'll leave it for the notes. Okay. We also started talking about the fact that all the intuitions that we built initially were for 2D convolutions on 2D objects or matrices, but really the operations being performed are 3D convolutions because there's a third dimension. The input dimension has a channel size C1, and so the filters, even though we may only talk about their spatial dimension, also has a channel dimension to it. And what we're really performing is convolutions by sliding in 2D, but we are multiplying two three-dimensional objects, the filter or the parameter or the kernel with the crop of the image or the feature or the activation or the input coming to this layer from the previous layer. So that's what we're treating as convolution. This object, this three-dimensional object, is called a kernel or a filter or weights or parameters in a convolutional layer. And what we will produce as output it will be an activation map or a feature map, which has channel dimension equal to the number of filters. So if we have multiple such three-dimensional objects, we will end up with multiple such channels. And so, for example, if you have 6 filters of size 5 by 5 by 3, you will end up with 6 as the output dimension, the number of channels as the output of this layer, which will then serve as input to the next layer. And this choice of 6 is a design choice. Okay, so that's where we were. Let's start diving deeper into some of the concepts that we wanted to understand, the concepts in particular around stride and padding. Okay, so let's take a closer look at spatial dimensions, and let's try to really understand that now. So we've been sort of hiding away spatial dimensions by saying, don't worry about it, we'll get to it. And this is now when we get to it. We started with a 32 by 32 by 3 object, and we ended up with a 28 by 28 by 1 in this case, but really the spatial dimensions reduced. And the reason why spatial dimensions reduced is we said, we want to place the filter inside valid locations. So let's take a look at that and what is that expression. So this is, for example, what that would look like for a simple object. So let's assume we have a 7 by 7. So N1 by N2 are both, N1 and N2 are both 7. We have a 7 by 7 input. And we're simplifying. We're not showing you the third dimension, the channel dimension, just so that we can understand the spatial dimensions. And let's assume a 3 by 3 filter. So this right here is my 3 by 3 filter object. We've been telling you that we slide it 1 over at a time, right? So this is slide number 1, slide number 2, slide number 3. So first of all, this operation of sliding 1 at a time, this right here is called a stride. And we are showing you stride equals 1, which means that you do not skip any pixels. You shift the filter over exactly 1 pixel over. But there's nothing in particular that holds us to that stride. You can actually define stride equals 2 or stride equals 3. So at stride equals 1, we got a 5 by 5 output because we did not want to place this filter outside the bounds of the input. So it is the choice of stride that is leading, and the choice of placing it at valid locations that's leading to this particular output. Let's consider what it would be for stride equals 2. It's the same sized filter. Now it's a 3x3 filter. Stride equals 2 just means that for any particular pixel that we're tracking, the next location is not going to be 1 over, it is going to be plus stride over. So we are going to place this pixel here and then here. So this is the first placement, I mean the second, this is the first placement, this is the second placement, and this is the third placement. And so to every row and column iterator or index, we are adding plus stride. And that's the sort of counting mechanism. And notice that at stride equals 2, we are getting a smaller output, a 3x3 output, because naturally we are skipping over placements in between, and so we get a smaller output. Okay, and now let's try to do this for stride equals 3. So first of all, realize that, you know, for any particular pixel, if this is where it is, I skip 2 over, this is one next placement, this is another next placement, this is the third valid placement, and now we have a problem. We actually cannot do stride equals 3, because that would result in this filter being placed outside the bounds of the image or the matrix. So the input dimension constrains what sort of strides we can use if we are choosing valid convolutions. If we want convolutions to always be filters to always be placed within the bounds of the image and exactly fit within the bounds of the image, the input dimension constrains what sort of slides we can use, the strides we can use. Okay, so we have stride equals 2 perfectly fine. Stride equals 3, we're running into problems. We actually just can't define stride equals 3 for a 7x7 if we want a valid convolution, because it leads to a placement that just doesn't fit. You cannot place a 3x3 filter with a stride of 3 in a 7x7 input. And so now we get to introduce this notion of a general sort of object of what sized output should you get with what sized input. So if you have an n by n input with an f by f filter, the expression for the output size is n minus f by stride plus 1. And the reason, the way you can, you don't have to memorize this, so you can usually see this expression happening, is that you track the last pixel. It's going to make some number of hops depending on your stride and your input size. And then if it is a valid convolution, it has to land on exactly the last pixel in the image. And so this distance is n minus f. That's the distance that last pixel has to travel, and that has to be proportional to stride. So the number of hops or that this filter makes is n minus f divided by stride, and the number of placements of the filter is number of hops plus 1, because at the very first placement, that's also a valid placement. So and that's how you get this n minus f by stride plus 1 expression. So if we're starting with a 7x7 filter, a 7x7 input and a 3x3 filter, at stride 1, 7 minus 3 by 1, you get 5x5 outputs. At stride 2, 7 minus 3 by 2, you get 3x3 outputs. At stride 3, it is just not divisible. So the expression is telling you that because you're getting non-integer outputs, valid placements are just not an option. So you cannot perform this convolution till you introduce this new concept of padding. Okay. So, but coming back, now that we understand stride and what's its impact on spatial resolutions, you realize that without padding, repeated convolutions with filters that have non-trivial spatial size will lead to reduction in spatial resolution. So just repeated convolutions will lead to reduction in spatial resolutions. And so if you do not want that, if this reduction is happening too fast, this reduction, if you do not control it, limits the depth of layers that you can stack in your neural networks, and you may be losing resolution too quickly. And so there are ways of controlling it. And so the common way of controlling it is to zero pad the border. Notice that this object right here that I'm drawing in the red, that's your original image. It's shaded in white, and there is a zero padding of one pixel around equally around the corners. And so now let me ask you the question: the input, a 3x3 filter was applied with stride 1. We padded it with 1 pixel border. What is the output size? Do people want to answer that in the chat? 7x7 input before padding of 1 pixel is applied, 3x3 filter, stride 1. What is the output? The reason why you can tell it's the same size is you've effectively converted n by n into n tilde by n tilde, where n tilde is equal to n plus twice equals 1. Because you've added in both one above, one below, one left, one right. So there's twice its effect that has been added. And if I just plug in n tilde in this expression, I guess I get n plus 2 times pad minus stride plus 1. In this case, 7 plus 2 times 2, 4 minus 5 by 1 plus 1. I'll get and that's the reason why it's the same size. And in general, you'll notice from this expression, if stride equals 1, you'll get this expression that, setting pad to f minus 1 over 2 will give you equal sized outputs, because it will basically cancel out the effect of the negative 1. And so you will get same n by n outputs if you pad with this factor, f minus 1 over 2. Okay. So that's where we're at. We know how to now prevent aggressive shrinkage of the output size. 0 is an arbitrary choice. You can ask the question, why 0? Why don't I pad with 1? It doesn't matter. If you pad with some constant value, then that is non-zero, then all you're doing is playing because it's a constant value that's getting added to every single boundary pixel. 0 is simply a convenient choice. There's no right answer here. So that's where we're at. We can control output size. And in general, it is common to see convolutional layers with stride 1, filter size f by f, 0 padding with f minus 1 over 2, which will preserve spatial size. So at 3x3, you'll get a 0 padding of 1. At 5x5, you'll get 0 padding of 2. At 7x7, you'll get 0 padding of 3. That's a pretty common choice. Okay. Example time. Let's do this as a question. Let's say I have an input volume which is 32 by 32 by 3. So here are the spatial dimensions: 32, 32, 3. This is C1, and I have 10 5 by 5 filters with stride 1, pad 2. And so the question is, what are the spatial dimensions and channel dimensions? So what is M by M by C2? And you can paste your answers in the chat, but one hint I'll give you is that C2 is pretty easy to tell. That's right at you, but you can take a couple of seconds. If you just want to respond with C2, that's fine. If you want to respond with the entire triplet, that's fine too. I see some answers already. 32 by 32 by 10, 32 by 32 by 10. Yep, that is correct. So the 10 part is pretty easy. That's just coming directly from the fact you took 10 filters. You take 10 filters, you're going to get 10 of those as the channels as the output. we used 5x5 filters, stride 1, pad 2. We on this slide that for 5x5 filters, f-1/2, you'll get a padding of 2 preserving spatial size. So we'll get 32 by 32 by 10 here as the output. Okay. Output volume size is, as we said, 32 by 32 by 10. Another question here. We're still in the same regime. We have 32 by 32 by 3 input. We have 10 5x5 filters with stride 1, pad 2. What is the number of parameters in this layer? And you can take a couple of seconds to think about that. Remember that this is 32 by 32 by 3. We are producing output, which is also 32 by 32. Now here 10, and we have 10 such filters. We have actually given you an expression in past, which has to do with K1 by K2 filters, and there were C1 input channels, C2 output channels. So what is the total number of parameters here? Now that I've told you that bit of information, that 760 is the right answer, not 750, think about where you may have gone wrong in your calculations. And typically where people go wrong is a direct consequence of the way it's taught, which is I don't talk about bias because it's just in there. And yes, that's exactly what's going on. You have 5 by 5 by 3 objects. Those are your filters, right? But you also have a bias, and there's 10 of them. And that's what gives you, here in this case, 76 times 10 equals 760. There is one bias corresponding to each filter, obviously. There's 10 filters, and that's why you have 760 total parameters. Okay, so +1 for bias. All right. To summarize, a conv layer, accepts a volume W1 height by width by some dimensionality. There are 4 parameters that you have to specify. You have to specify number of filters, spatial extent, their stride, and the amount of padding you want. Notice this is exactly why people don't talk about the channel dimension, the input channel dimension, because you don't get to specify that in that layer. It's just specified based on what sort of volume you are accepting as input. And some common choices for K, which is the number of filters. It's in powers of 2, but really it's about how many neurons do you want in a fully connected layer, for example? This is a similar question. How many channels do you want as the output? And it's very common to have 3 by 3, 5 by 5 filters. If you're coming from a signal processing background, it is natural to think, obviously, that you will want odd-sized spatial dimensions because you think of the origin as lying in the center. But notice that in deep learning, there is no reason to have any notion of symmetry in the filters with the center pixel being special. So it is actually possible to have 2 by 2 filters. It is possible to have even by even sized filters. It's just odd, but it's certainly possible. Implementations will allow it. You just have to make sure that if you want valid convolutions, what you want. If you are going to do padding, it just becomes an awkward calculation where you pad on one side and don't pad on the other if you want the same size outputs. But it's certainly possible. You will see it in some implementations where they'll have 2 by 2 filters, for example. Certainly possible. Okay, so now that we've looked at stride and padding, let's look at an interesting question of 1 by 1 convolutions. And so this is an interesting question. Can we actually? I said we are in this modern deep learning regime. We can have even-sized convolutions. Can we have 1 by 1 filters? Can we have spatial dimensions equal 1? If you pose that question to a signal processing person, 1 by 1 filters are just weird. Like, why would you even want a 1 by 1 filter? That does nothing. It's just a scalar product. Because if you think about it, for a 2-dimensional object, if you have X here and W here, which is a 1 by 1 object, I'm not drawing the spatial dimension now. I'm just talking about 2-dimensional signals, and we'll talk about channel dimensions in a bit. If W only has 1 by 1 spatial dimensions, all that you're saying is that in order to compute Y 0, 0, I put this, one-dimensional, one-by-one object on the input, and there is no need to do any enumeration or summation. All that happens is y 0, 0 is x 0, 0 times w 0, 0. And you just keep repeating that at all locations, and the expression tells us that analytically as well. YRC, we remember we're summing over spatial dimensions k1, b going from 0 to k2 minus 1, x r plus a, c plus b, wab. That's how we were defining convolution. Well, if k1 and k2 are both 1, this summation basically goes away. There's just one expression here, and that's x r comma c w 0, 0. So it's basically take your input x, there is a scalar, multiply every pixel by that scalar, and that's how you get that output. So one-by-one convolutions don't make any sense. You don't need to implement them as convolutions. You just write them as for loops, or you're basically multiplying every pixel by a scalar. But from a deep learning perspective, it is perfectly valid to define one-by-one convolutions. It is a lot of times useful to define one-by-one convolutions. And that's because one-by-one convolutions are just telling you about the spatial dimension. They are not telling you about the channel dimension. We have, let's say 56 by 56 by 64 dimensional input. When I say one-by-one convolution, what I really mean is I have 1 by 1 by 64 is the object that I'm constructing, right? And I'm drawing the third dimension horizontally, and so there's really 64 numbers in my 1-by-1 filter. There is not just one number, and what I'm doing is I'm placing those 64 numbers at every pixel, and I'm multiplying. And so it's not just multiply every channel with a scalar, it's multiply every channel with a scalar and then add them in that combination. So it's a linear combination operation that I am getting as the output of these channels. So what one-by-one convolutions are doing is that they're giving you a linear combination of existing filters, and so now you can do dimensionality reduction or dimensionality increase with one-by-one convolution. If I pick, for example, 32 one-by-one convolutions, I will reduce my channel dimensions from 64 to 32, keeping the spatial dimension exactly the same. I don't need any padding. I don't need, no spatial dimension will be lost. But if I choose 128 as the number of one-by-one convolutions, I will end up increasing my spatial size. So I could also make this 128 if I just chose a different number of one-by-one convolutions. So really, one-by-one convolutions serve as a way of shimmying data from one layer to another. If there is something downstream where you want it to be a particular size, there's something upstream that's producing a different size, think of one-by-one convolution as a way of just performing dimensionality increase or reduction in the channel dimension. Okay. All right. And of course, interestingly, you can think of fully connected layers as one-by-one convolutions. So you can just think of fully connected layers as really weird images that are one-by-one spatial size. And I can take every single pixel or every single feature dimension, and I can write it along the channel dimension. And then I can think of my weights as also one-by-one and stretched out along the channel dimension. And this is a very weird convolution. It's a one-by-one input being convolved with a one-by-one filter. So there's no spatial movement at all. And it's just performing dot products at this point. It's just a weird transpose. We're playing around with the 3D rotations and transposes to get to write down a fully connected layer as a one-by-one convolution. Okay. All right, so we've looked at these two things so far, and next what we'll look at is backprop in convolution layers. And let me just see if there are any questions at this point. Okay. All right, so as I said, we are dealing with computational graphs where we think of these things as Lego blocks. Now we have a new Lego block to play with. There is a convolution layer that is a new Lego block. It accepts a tensor as input, it produces a tensor as output, and all we need to do is define, reverse mode automatic differentiation or Jacobian times gradient multiplication for this particular layer, and we're all set. We can implement backprop in this computational graph that now contains a new kind of layer. As I said, the key computation we'll need to define is forward prop and backward prop in a convolution layer. Everything that we've told you so far, what convolutions are, was defining the forward prop in a convolution layer. Now all we have to do is define backprop in a convolution layer, and if we can do that, then reverse mode automatic differentiation will figure it out in the convolution in the directed acyclic graph. So let's do that. I want to mention that this is clunky and it's very notation heavy, and for whatever reason there is no sort of authoritative source of there's no authoritative version of this derivation. It's the standard sort of machine learning books, for example, Kevin Murphy's book doesn't contain a derivation of backprop in convolutional layers. Even the deep learning book by Ian Goodfellow, Aaron, and Joshua doesn't contain a derivation of backprop. And so I have a set of notes that when I first created this class a few years ago, 2015 at this point, I just sat down and basically pieced it together and derived the thing. And so that's what I've been teaching with. You're welcome to go through these notes. I will do one direction of the derivation. It's heavily simplified. The purpose is to build intuition. You will, in practice, never be writing backpropagation in a convolution layer yourself. Most of you will just be making calls to PyTorch and built-in implementations. But I think it's really useful to work through it with pen and paper and actually implement it from first principles. It gives you a sense of understanding that is difficult to get if you're just using a black box. Okay, but with that sort of caveats, let's get started. So we'll make a couple of simplifications. So we have a convolution layer. The simplification we will make is, look, we will have to reduce, subscripts and superscripts. They get quite clunky. We already have a bunch of indexers into rows and columns that we will need. So we'll try to keep this simple. We will say that C1 equals C2 is equal to 1. There's one channel input, one channel output. It doesn't really make a difference to the derivation, because if you wanted to do this for more channels, there's just another summation that gets added in the forward pass, and there's another summation that gets added in the backward pass. So let's consider the simplest case. And let's not overload the H notation with the HL and the HL plus 1. I will keep it simple by saying, there's an input X, it produces an output Y by taking the filter W. And I will also not get into the messy sort of padding notation by saying X is N1, N2, W is K1, K2, and we have done whatever we needed that we are getting the same sized output. So there's padding that's already been done, appropriate padding that's been done. Okay, so this is just to keep things simple. Notice that backprop as input will give us the partial of the loss with respect to Y. This is an object of size N1 by N2. And what we have to implement, or what we have to derive first, is how do we get the partial of loss with respect to X so that this propagates backwards to other layers? And how do we get the partial of loss with respect to W so that this object we can use for gradient descent? And this is the sort of key computation that we need to do. Okay, and so this is object number 1 that we need to compute. This is object number 2 that we need to compute. I will show you how to compute object number 1. I will do that derivation in class. For object number 2, I encourage you to check out these slides, these notes. They contain the detailed derivation. Okay, so let's take a look at that. So the object that we need to compute is the partial of loss with respect to W. Okay. Now this is obviously a matrix because L is scalar, W is a matrix, and so we will index into this object using A prime and B prime notation. Why are we using primes? Why not without primes? Well, because we've already used A and B to define the iterators in the convolution expression. And so this is why it gets tricky. We need two sets of iterators, one that defines convolution in the forward pass and one that allows us to index things in the backward pass. Okay, so we have a X, we have a W, and we have a Y output. Now the question that I will ask is, look, there is some filter, there's some pixel A prime and B prime in W. The chain rule tells me that all I need to think about is, during the backward pass, I have as input during backward pass the partial of loss with respect to Y. I already know this, and I have to produce as output the partial of loss with respect to the W. That's my goal. If I already have this as input, all I need to think about is how does W affect Y, and how does Y affect the loss, because the input is already telling me that. So one way of writing this informally is to say, chain rule, I will sum over all pixels P in Y that are affected by W A prime B prime. So if epsilon perturbations to W A prime B prime change that pixel value, then I will consider it in this summation. And it could be that in this direction it turns out that actually I'll let me finish this expression, then I'll ask you. So this is loss by YP for that pixel and YP with respect to W A prime B prime. So far this is just chain rule. I haven't done anything fancy. I know that I'm just considering, let me use another color. So this right here is my input in backprop, and this right here is a component of the layer Jacobian, right? It's an entry in the Jacobian. So that's what I have to implement now. So first questions first. Let's just deal with this mess right here. Pixels affected by W A prime B prime. So question for everyone. What are the pixels in Y? So notice this is the Y object, this is W object, this is X object. What we're asking is, if I go to W and I make epsilon perturbations to W A prime B prime, meaning that I add in plus minus epsilon, which pixels in Y do you expect to change? So let me first ask Y0, 0. Do you expect Y0, 0 to change if I make epsilon perturbations to W A prime B prime? Any guesses? And yeah, I am already getting answers for the other question, which is all pixels. All pixels are affected, but by consequence of that, I assume that people see that Y0, 0 is indeed affected. So yes, all pixels will change. Yes. Okay, yes. So that is correct. So Y0, 0 first of all will change, because what you do is you place this filter W on top of, in order to compute Y0, 0, you place it at X0, 0 location, and therefore this A prime, B prime number multiplies X A prime, B prime, and therefore that shows up in this calculation. So first of all pixels are affected. The reason why I did this is, this is one direction. In this one direction, the answer to the summation is all pixels are affected. When you do the other direction, which is loss with respect to X, all pixels are not affected. There's a small number of pixels that are affected due to the spatial local connectivity of W. So, okay, all pixels are affected. That's good. So I can replace this summation by a couple of iterators. So I can say, R equals 0 to N1 minus 1, E equals 0 to N2 minus 1. Okay, that part's clear. Now, so this part is easy. This is just, we know that this is given to us, loss of y r comma c, partial of loss with respect to y r comma c. I've just replaced that one term. So now what we need to do is we need to compute the second term. What is the partial of y r comma c with respect to w a prime comma b prime? And so that question is really asking, just like we did for this w0 comma 0, if I picked some pixel r comma c, in order to compute it, I would go and place this filter at the r comma c location. So this is now the r comma c location, and I would ask, as I make changes to w a prime comma b prime, how does y r comma c change? Okay, and the way to do this is to, you can do this pictorially. You can try to reason that this is the dot product. We can also just sort of do this analytically. And let me clean up some space here so I can do this analytically right here. So this object is y. Let me remind us of this expression that y r comma c is equal to a equals 0 to k1 minus 1, b equals 0 to k2 minus 1. And notice these a and b are different from the a prime and b prime. This is why we needed the prime notations of x, r plus a, c plus b, w, a, b. And now the question we're asking is, I come in and I ask you, what is partial of this quantity with respect to w a prime comma b prime? So in this summation over all pixels, where does, for example, w a prime b prime appear? Right, that's the question that I'm asking. So this expression is clearly linear in w's. Somewhere there is a w a prime b prime, and I'm asking what is the slope of that linear function. So thoughts? What is partial of y r c with respect to w a prime b prime? X r plus a prime, c plus b prime. So it's not really about x. Yes, we know something about x will show up, but it's really just calculating indices, like which indices matter. R plus a prime, c plus b prime. Yes, exactly. So this is an expression that is going over values of a and b. At some point it will hit a prime and b prime. That's the only thing that depends on w a prime b prime, and so we will just pull out that multiplier. Everything else in this summation does not depend on w a prime b prime. And if you're having sort of difficulty, just sort of think about this in your head. Think about a prime b prime being something like 0, 0. Like, what is w0, 0? And so, well, there's this summation happening. So one of those terms is w0, 0. Everything else is w0, 1, 1, 1, whatever. It doesn't depend on w0, 0, right? So what pops out of this expression is r plus a prime c plus b prime, right? That's what this object is equal to. That's what the gradient, that's what the partial is equal to. Okay, so first so good. So all I need to do is I need to plug that into that expression. So this object right here is equal to x of r plus a prime, c plus b prime. So I just need to plug that in it. I will switch slides, but I realize that once you do a lot of writing on one slide and then you switch it, it's like almost like a memory being wiped clean. So let's remember that the only thing I will copy to the next slide is this expression, w a prime comma b prime. So try to keep this expression in your mind. I will rewrite it. This is what we will analyze on the next slide. Okay. So the partial of, all gone, everything forgotten. The partial of loss with respect to w a prime b prime. There's a summation over r equals 0 to n1 minus 1. Summation over c equals 0 to n2 minus 1. There was a partial of loss with respect to y at rc, and partial of y. Oh, I don't need to rederive it. Sorry, muscle memory. And x of r plus a prime, c plus B prime. Okay, I've just copied things over. And so now, we're almost done. The question for you is, does this expression remind you of something? I am telling you that there is this backprop object I'm calculating. If you want to know the A prime comma B prime value of that backprop object, you have this double summation over the spatial resolutions of this term times this term. Does this remind you of something that we've been doing in this class, in this lecture, this entire time? Does this look like an operation? And hint, hint, there aren't too many operations that we've been looking at. Yep, convolution. This is a convolution, and if you're having difficulty seeing it, just swap these two terms, right? So remember, our convolution definition was YRC is equal to summation of A equals 0 to K1 minus 1, B equals 0 to K2 minus 1, X R plus A, C plus B, W, A, B. That's the definition of a convolution. And so really what this thing is that the partial of loss with respect to W, now we're just doing pattern matching. There's an X-like object showing up, and there's a W-like object showing up. And so the partial of loss with respect to W is X convolved with the partial of loss with respect to Y, with appropriate padding. And I will write, with appropriate padding. And the reason why I need to write that in a couple of seconds, it becomes clear. X is X is an N1 times N2 object, and we had said that the partial of loss with Y was also an N1 times N2 object. And so if you try to convolve them without any padding, you'll just get a scalar output out. But if you pad it by K1 minus 1 over 2, K2 minus 1 over 2, you're going to get an object of size K1 times K2. Which is exactly what this object is. So with appropriate padding, back propagation in a convolutional neural network, at least in this one direction, is the convolution of the input with so X with the gradient coming back, and that's how you get the thing. And so notice that there's a nice little duality happening here. In the forward pass, it's a convolution. In the backward pass, it's a convolution. And turns out that if you look at the other direction, the partial of loss with respect to X, that is also a convolution. It turns out not to be a convolution with X. It turns out to be a convolution with W. It ends up being W slightly modified. You have to sort of flip the filter about its center. You can also think of it as a 180-degree rotation of the filter. It shows up just because the rotation and the flipping shows up just because of how the notation sort of works out and the way the operations are defined. And like there's a very nice analogy to fully connected layers. Just like fully connected layers in the forward pass were matrix multiplications from the right, matrix multiplications from the left, and it was a dual operation, we end up with exactly that same sort of duality happening here. That you take your, if you want to know what is, W, what is the gradient with respect to W, take your input X, convolve it with the gradients. And if you want to know what is the gradient with respect to X, take W and convolve it with the gradients. And that it's a generalization of dot products and linearity, if you will, where you get this expression. And hopefully you have somewhat of a good intuition for backpropagation in convolution layers. I highly suggest going back and looking at the notes and just sort of maybe trying to derive this, in parallel by yourself. By keeping those notes maybe in front of you, but trying to do this yourself. Okay, so the next thing that we want to get to are pooling layers, and we already received a question about this earlier in the class. So let's take a look at what pooling layers are. It is really common in CNNs to have not just convolution layers, or in convolutional neural networks, to not just have convolutional neural conv layers and ReLUs, of course, but also these things called pooling layers. Let's try to understand them. After that, we'll try to understand this transition from convolutional layers to fully connected layers. And at that point, we'll be done. We will have understood all components of a CNN and how to put it together. So the key intuition for a pooling layer is that we need to gain some robustness in the computation that we're doing. So the intuition for pooling layers is to think of, every channel or every filter, three-dimensional filter, as looking for some kind of feature. And we showed you what sort of features and what sort of patches various neurons in a convolutional neural network respond to. So let's in that spirit, let's think of one filter as an eye detector. We are not certain that eye detectors will emerge, but it's just a thought exercise. So let's say the particular weights that we have W at this point correspond to trying to detect eyes. So this is HL minus 1, which is or HL at this layer, which is producing these activations. What we want is some sort of robustness. It shouldn't matter exactly where the eye fires in this general neighborhood. And the way to do that is to say, to pool the responses, for example, taking max, taking average, or any other operation at different locations, and this gives us robustness to the exact spatial location of the features. So it doesn't really matter if the eye in the image was located here or here. Wherever it was located, one of these 9 pixels will have high value, and the others will have low values. But if we are taking a max of these 9 pixels to get this, so this is HL minus 1, this is HL, and this is HLR comma C that we're defining. So if we take a max along this, we will gain certain robustness to where it fired exactly. And so this operation right here is a very specific pooling operation or a max pooling operation. And it's important to note that pooling layers make the representations smaller along the spatial dimension. They typically do not reduce channel dimensions. So this is a pooling layer where there were 64 channels in the input. There are still 64 channels in the output. We take every slice of this 3D tensor. So this 3D tensor is a 224 by 224 spatial object. You can think of this pooling layer as a downsampling operation that we're going to put back in that same location. So the ordering of channels has not changed, nothing has changed, just the spatial resolution has reduced. And so, so far you've been hearing me say that, we don't want to lose spatial resolution too quickly. Pooling is a way of losing spatial resolution. What's going on? Well, we're just giving you the tools to deal with data in various situations. In some situations, you do want to gain robustness and you're okay with losing spatial resolution. In other situations, you want to control loss of spatial resolution, and so you will not have high strides in those things. The interesting thing is that I can think of pooling as a very weird convolution-like operation as well. So for example, this is a single depth or channel slice. What I can do is I can define, this as my X, and I can define a particular pooling operation. So this is Y, and I can say that, Y of R comma C. Now, instead of summing over some range, I can say this is a max over A in 0 to 0 comma 1. Like I can have an iterator, B in 0 comma 1. And I can say this is max of X, R plus A, C plus B. There is no W, there is no multiplication, but I just sort of take my filter. It says 2 by 2. If I'm doing 2 by 2 pooling or with 2 by 2 filters, I place my filter. There is no actual parameter there, but I just consider a window of 2 by 2 at the 0, 0 pixel location, and I consider these 4 pixels, and I store the max value here. Then I slide it over by a stride of 2 to place it at this next location, and I take the max of all of these and I place it at this pixel, and I repeat this. So it's a convolution-like operation, but it's not convolution because it's not a linear operation. There's no dot product and summation happening, and this is much more like a ReLU-like operation in 2 dimensions, except we're defining it spatially. And now, if you remember, there was a question earlier in the class about can we have overlap in the stride of these max pooling filters? And yes, you can. Typically, you do not have overlap in these filters. Typically, you define the stride equal to the filter length so that you basically have are doing exact reduction in spatial dimensions. But if you wanted to do a partial reduction by some factor, it's fine to have overlap. But typically there isn't. And so this is just a larger, for example, 4x4 object with a 3x3 neighborhood over which we are doing max pooling with a stride of 1. And now in this GIF, we're also adding padding. So everything that we've learned for convolutions, the padding notation, the stride, we can apply the same thing for max pooling as well. So this is, we've converted a 4x4 input with a padding of 1 with a stride of 1 in this case. So that the output, the same sort of, the expressions that we wrote down for input output sizes, n minus, n plus 2 pad minus f by stride is plus 1 is the output size. Those expressions are still valid for doing calculations of input and output size. Except we're not doing dot product and summation or element wise product and summation. We're just taking a max of those things and storing in the appropriate locations. And this was all max pooling, which defines a max over a neighborhood of rows and columns, but you do not have to be restricted to max pooling. You can do mean over that neighborhood. You can do L2 norm pooling over that neighborhood, and a number of these expressions are perfectly valid and well defined. Max pooling is what is typically common and shows up, but on any of these expressions are fine. One thing I want to use this pooling step for is to convey the notation, convey the concept of receptive field, which is a very useful concept. So let's assume we have a convolution layer followed by a pooling layer. So going from HL-1 to HL to HL plus 1. And so this is, for example, one of the channels in the HL-1. We notice that there are some pixels, that are involved in the computation of this one pixel on the output. And remember, we made an argument that the whole entire point of convolutions arise as a result of local connectivity. That there is a small number of pixels that affect the computation of this one pixel, but as soon as you have pooling, you realize that any of these 9 pixels, any of these, 4x4, 16 pixels affect the output at this one pixel at the next layer. So this is HL-1, this is HL, this is HL plus 1, a slice in HL. So this is one pixel in HL plus 1. And we notice that as a result of pooling, you have a larger set of pixels change in which this pixel value changes. And this is quite common. When you stack together convolutions or you stack together convolutions and pooling, this notion right here is called receptive field. A receptive field is the set of pixels that affect the value of a particular pixel R, C in a layer L plus 1 or L. So you pick a particular pixel and you pick a particular layer. The set of pixels in the input, for example, that affect this pixel's value is known as its receptive field. That is the portion of the input that this neuron and this pixel looks at. And stacking of convolutions or stacking of pooling increases the receptive field. So if you have a F by F filter in the convolution layer with a stride of 1 and a P by P pooling region in the pooling layer, you get P plus F minus 1 times P plus F minus 1 as the receptive field in this new layer. And this is quite common for people who have taken sort of signal processing classes. You know that this P plus F minus 1 expression is coming from the support of two filters that are convolved with each other, and so this is that expression, and it gets additively added as the region. And so very quickly, as you go deeper into these neural networks, you get receptive fields that are large enough to be the size of the entire image. So very quickly, the entire image plays a role in the computation of a particular pixel at a layer. Okay, and so that's where we are with pooling layers. So pooling layers are kind of like convolution layers in their API. They also accept volumes. We define a spatial extent and a stride just like we would for convolution layers. And you go through the same sort of calculations for the stride and the input-output sizes. Stride of 2 is pretty common with this filter size of 2. 3,2 is also pretty common, and you get the same calculations. Notice that there are no parameters in this layer. It computes a fixed function. You can backprop through it, of course, and you have to in order to backprop, but there are no parameters to be updated. So you do not need a del L by del W. You don't need that. Okay. So let's stop here, and next time we will look at this first transition from a convolutional object to a fully connected object, and that is the one sort of special thing that requires a bit of careful treatment. And at that point, we will basically be done with sort of developing CNNs.